The topic is uniform charge sphere. In this, we use a Gauss's law to determine the electric plug density capital D due to this uniform charge sphere. For this, we consider a sphere of radius small a having a uniform charge density rho naught. Unit is coulomb per meter cube, means this is a volume charge density actually. The volume charge density of this sphere is rho naught. Now, this is a spherical symmetry. The charge has a spherical symmetry. So we apply a Gauss's law for two cases. First, we consider a point P inside this sphere, that is R less than or equals to A, and second case R is greater or equals to A, means in first case we consider a point inside this cube, and second we consider a point outside this uniform charge sphere. So one by one we talk about these two cases. The first case is R less than or equals to small a. Now we consider a sphere of radius a here, and the first case is R less than or equals to a. We take a point P inside this sphere having a distance r, small r, and we assumed a Gaussian surface that passed through this point having a distance r. Now, according to Gauss's law, Q enclosed equals to rho v into dv. Rho v is the volume charge density, and the volume charge density of this sphere is rho naught, which is given. So we get only rho v in volume integration of dv. Volume integration dv is a triple integration, and the dv in case of spherical coordinate system is r square sine theta dr d theta d phi. So here we take a triple integration, first with respect to r, second with respect to theta, and third with respect to phi. The limit of r is 0 to r because we take a point inside this sphere, and the total charge according to Gaussian surface is within this radius r only. So the limit of r is 0 to r only, and the limit of theta is 0 to pi in case of spherical coordinate system, and the limit of phi is 0 to 2 pi. After making this arrangement, means we take r with dr and sine theta with d theta, and calculating this integration, we get rho naught 4 upon 3 pi r cube. Now to simplify the Gauss's law, we take a flux also, total flux. The total flux size equals to closed surface integration d dot ds. Now here the vector d has only r component, and its direction is towards unit vector r, and at this point we consider a small differential surface, and its direction is also in the direction of unit vector r. The dot product of two same vector is 1. So we get a closed surface integration of ds. So in case of spherical coordinate system, the closed surface integration of ds in the direction of unit vector r is r square sine theta d theta d phi. So here we take a double integration, first with respect to theta and second with respect to phi. The limit of theta is always 0 to pi, and the limit of phi is always 0 to 2 pi. After calculating this, we get dr 4 pi r square. Now we equate phi equals to q enclosed because here we apply a Gauss's law. After substituting, we get dr component that is equals to r rho naught upon 3, and in terms of vector d equals to r upon 3 rho naught in the direction of r. The r is from 0 to a only. And in second case, we consider a point outside this sphere. Here we consider point P outside this sphere having a distance r. At this point we assume a Gaussian surface. Now this Gaussian surface acquire a total sphere, means total charge. So this Q enclosed is equals to rho v into dv. The volume charge density rho v is equals to rho naught, that is given. And here the volume integration is equals to triple integration. Now here the point to be noted means the limit of r. The limit of r is 0 to a only because the charge is the uniform charge density is only from 0 to a. So the limit of r is 0 to a only. So after calculating this, we get rho naught 4 upon 3 pi a cube. Here the flux I is equals to closed surface integration d dot ds. The vector d and ds has the same direction, so the dot product is 1 and we get only dr component, and the surface area of the sphere is 4 pi r square. The sphere here, the sphere is Gaussian surface. The radius of this Gaussian surface is small r, and the surface area of this Gaussian surface is 4 pi r square. After equating this, some quantity can be cancelled. So dr component is equals to 1 upon 3 a cube upon r square rho naught. This is the magnitude part, and in terms of vector, d is equals to a cube upon 3 r square rho naught in the direction of r. Here r is greater or equals to a. So in general, we can write the two cases combined. First, for r greater or equals to 0 less than or equals to a, and in second case r greater or equals to a. So this is a general electric flux density in case of uniform charge sphere. We can also represent graphically the relationship between magnitude of vector d versus distance r. Now from first case we see here that the magnitude part of vector d is r upon 3 rho naught, and it is a magnitude, and you can say that the vector the d is directly proportional to small r, since rho naught upon 3 is a constant value. So d is directly proportional to r, so the graph is linear, and in up to a, and at a the value of this d is a upon 3 rho naught. In place of r we can write a upon 3 rho naught. Now after this a, we see here that the d is inversely proportional to r square. So it is non-linear graph, and at r equals to infinity, infinity means 1 upon infinity, that is 0. So the graph is tend towards 0 at infinity. So this is a graph between magnitude of vector d versus distance r.